Okay, good morning. Last time we discussed the analog compression and expansion. You still remember this? So you know how to do it, right?
Yeah.
The compression occurs before we do the PCM coding. After we compress it, then we PCM code. Today we are going to discuss digital companding, means digital compression and expanding. That means once we sample to get the discrete data, we, as usual, just compress it, then we get a PCM code, for example, 12 digit. Before we transmit, we compress it. For example, we compress from 12 digit into 8 digit. Then we transmit same thing at the receiver. Before we do the DA conversion, we need to do expansion first. To recover the 12 digit from the 8 digit, then we do the digital to analog conversion. First line, let me give you ask you a question. In binary, I'll give you a binary number. How do you do to divide it by 2? For example, I give you a binary number, 1010, okay. I want you to multiply by 2, how to do it? I want you to divide it by 2, how do you do it? Let's discuss first. Multiply by 2.
2, 4, 8, 6.
Yeah, I'll give you a number, for example, 1011. Binary. How to multiply this by 2?
Convert it back to.
Convert it back to decimal. Oh, that's not fast enough.
Shifting it
Okay, shift. I like that word. Shift to
left.
to the left, to the right. To the left, right? That means I add 0 at the end. That's it, right? So this is the multiply by 2. So 100 multiplied by 2 equals, sure, this 2 it cannot be 2, right? So 10110. How about I divided by 2? Right? That's 2 again. That's 2 is decimal. How about dividing this by 2? Shift to the right. So I will get 101. How about this one? Just throw away. Yes, we just threw this away. Alright, that will be the error. Today we are going to discuss digital companding. Example is as we can use 12 digit bit, then reduce to 8 bit, then that will be reduce the line transmit rate. Line will reduce the line speed. Reduce the line speed. One example is called mu 255, 13 segment compression. Let me draw the curve first. The curve will be the curve looks like this. This still looks like a logarithmic in analog, right? Yes, it is very similar to the analog logarithmic in analog. But all this part will be straight line instead of a smooth curve. So this is called a piecewise linear. All this part between each segment will be a straight line. It's just piecewise linear. And this is 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. In other words, I approximate the logarithmic curve with this piecewise linear and divided this by into 8 segments. 1, 2, 3, 4, 5, 6, 7, 8. Well, I said 13 segments. Oh, those are the positives. Right? I have negatives on the other side. That 8 plus 8 gives us 16, but still not 13. Right, so here is the reason. If the number, so this is x, this is y, this is the input to the compression, this is the output to the compression. Right? If your number is small, what does that mean small? It means it is in the first segment or in the second segment. Then we just use we do not compress. This part will be the same. So just linear. You give me 1, I output 1. You give me 2, I output 2. If it's in the first segment and second segment, the output equals input. That means this will be straight line, this will be straight line. And this straight line will be also one straight line. Make sense? But for small signals, we do not compress at all. X equals y, so that's just like this. And these are the 4 positive numbers. For negative numbers, we go this way. They are anti-symmetric. They are the same thing, so like this. Right? So although we have a 8 plus 8, 16 segment, but this 4, 1, 2, 3, 4, actually just one segment. So 4 actually is 1. That means we reduce by 3. So 16 minus 3 equals 13. So that's the reason, right? So we have positive input, we have negative input, we have an anti-symmetric. But the middle 4 segment actually is only one segment. They are straight line. If your input value is between this, it's not that small, it's in this segment. So the 0th segment, the first segment, the second segment, if within this, then I'm going to divide the input by 2. Right? So this compression ratio equals 1 is 2 to 1. If you give me 6, the output equals 3. If you give me 10, the output equals 5. But you need to make sure that the input is in this segment. Right? And if the input is in this segment, then it will be a 4 to 1. Similarly, this one will be 8 to 1, and this one will be 16 to 1, and this one will be 32 to 1, and this one will be 64. And we have an anti-symmetric curve on this side. For negative input, we get negative output, but the compression ratio are the same. Any questions on this? Last time we discussed analog compression. We have that mu law or A law algorithm. We know all the maximum, the peak value, the parameter mu, and all those, and the analog discrete value we want to convert. So we just plug into numbers and we get the output. But here, we do not use that algorithm. We use this curve. And what we do is, first one, I give you an input. You decide where the input is on this segment. If the input is on this one here, then you just divided it by 8. Because we already know those are binaries. So divided by 8 means shift to the right by divided by 8 means shift to the right by how many digits? Divided by 2 means shift 1 bit. Divided by 4 means shift another one. Divided by 8 means shift 3 digit, right? To the right. So you just, like if the 1, 0, 1, 1, you divide it by 8, what do you have? 1, right? This 3 out, the big out. That's easy, right? And we don't need to do the calculation. You don't even need to know. You use calculator. Okay. Let's see. These are very typical. We have some other characteristics, but we are going to discuss this only in this class. Now we have an example. It's 12-bit to 8 compression. The rules are segment if on the first segment is 0th segment, and we said the compression will be 0, no compression. If the linear PCM code or the input is 12-bit is the first digit is the sign. Usually for positive numbers we are going to use 0. For negative numbers we are going to use 1. But some they may opposite. Right? Depends on the application. So in the homework I purposely give you opposite, so you need to be careful. In the homework I just positive, I let you use 1. Right? Usually you use 0 for negative, for positive, right? The first one is a sign. Then we have another 11 digit. Another 11 digit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4. It's not good enough. Lots of digits. 1, 2, 3, 4, 5, 6, 8. If the input is on segment 0, that means it is small. So how do we define small? If the 12-digit input has this kind of form. The first one is a sign, we don't care, 0 or 1, represent negative or positive. And we have 1, 2, 3, 4, 5, 6, 7 zeros. We have 7 zeros here. And the last 4 will be the input, will be the number, right? A, B, C, D. No matter they are zeros or ones, we don't care. We only guarantee that this 7 will be zeros.
What does that say besides?
F means sign.
No, besides segment.
This one,
Yeah.
linear PCM code.
Okay.
We want to compress. That means this is the X, the input. Right? Maybe it's too small. Let me write this. Right? Linear. That is 12-bit. In this example. For example, if I said the 12-bit is 0, 1, 1, 1, 1, 1, 1, 0, 0. So this is 1, 0, 0, 0, 1. Is this number small? Means is this one on segment 0? What you look at is the first one, you don't care, that is a sign. Usually that means this is positive or maybe negative, right? And 1, 2, 3, 4, 5, 6. I forget something. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, yeah. Okay. This is the sign. 1, 2, 3, 4, 5, 6. We need 7 zeros here, but this one is not 0. So that means this number is not small. That makes sense? Right. If the number is on the 0 segment, we need to have 7 zeros after the sign. Right? This one is not small. This one will be compressed. Right? We said we have no compression for this. So this is the number. So we are just keep this number. So we have the next one is the compressed. Compressed means 8. And we just keep A, B, C, D here. Alright, suppose this one here is 0. Alright, and I will use 1 here. Is this number small? On segment 0? Yes, alright? So this one is here. 1, 2, 3, 4, 5, 6, 7 here. And the last 4 will be the data, A, B, C, D. How to compress this? We said we do not have any compression for this one. So I will keep this. I'll keep A, B, C, D here. In this example, I'll just keep 0, 1, 0, 1. And the compressed code has 8 bits. So I will have 4 additional. Alright, the first one is the sign, so I just put the sign. No matter positive or negative, I just copy. Now I need 3 more. 3 more. This is on segment 0, right? Alright, I will represent 0 with a binary, so that will be 0, 0, 0. 0, 0, 0. So this actually is the segment, the representation for segment. So this one is small, which is on the 0th segment, so 0 means 0, 0, 0. Any questions on this? Alright, next one, if the number input is a little bit larger, and it is on segment 1, so on here, then segment 1, that 12 digit will be, again, the first one is the sign, and we have 6 zeros, 1, 2, 3, 4, 5, 6, and 6 zeros, and the next one will be, cannot be 0, right? So it must be 1 here. Then we may have some A, B, C, D here. Is this one on segment 1? Yes, right? But this one here. And the compressed value will be, and we said on the first segment, the first segment is 0 first here. We do not have any compression. We need to use the original number. Right? So the compressed is S sign first, right? And we have a 5 digit for the data. 1 A, B, C, D. So I just copy 1 A, B, C, D. That's it. Right? Now I have 5. Okay. I don't use this one. I still use A, B, C, D. But I will represent these 3 represent this 1 here. The 1 in binary is 3 digits is 0, 0, 1. So that is again segment. That segment is this segment. Any questions on this? Right? If the number is larger than this, so it will be on the segment 2, and the number will be S sign here, and 0, 0, 0, 1, 2, 3, 4, 5, 6 here, we have 5 here, and we are going to have 1, and A, B, C, D, and we are going to have some others, 0 or 1. We don't care, so this part. No matter it's 0 or 1, we don't care. So I'll put the X here. I have 1, 2, 3, 4, 5, 5 zeros, 6, 7, 8, 9, 10, 11, 12, 12 digits. If the number is on segment 2, which means it is in this form, in addition to the sign, we are going to have 5 zeros, then followed by 1. Then the next 4 will have A, B, C, D. We need to use that, so we use A, B, C, D. Then the last digit, 0 or 1, we don't care. I will just put an X here. The compressed value, can you tell me what's compressed? The compressed will be A, B, C, D here. You keep this. We don't care this one. This one is gone, right? On this second segment, the compression ratio is 2 to 1. That means we are going to divide the input by 2 to obtain the output. So divide by 2 means we shift this one to the left by 1 digit. To the right by 1 digit. So this x will be gone, no matter 0 or 1. So we have only A, B, C, D left. So A, B, C, D. And definitely the first one is the sign. Then I need 3 more. This 3 digit represent how large is the signal. That means which segment it is on. So what the segment? 2, right? So represent 2 with binary is
0,
0, 1, 0. Use 3 digit because we need only 3 digit. So 0, 1, 0. And this is the segment here. Okay, so that is compressed. Questions on that? Good? Easy, right? Just be careful. The next one will be, okay, the input is larger than this, so it will be on the segment 3, and S 0, 0, 0, 0, 4 zeros, and then 1. And again, we have A, B, C, D. Then we have 2 more digits. We don't care because the compression ratio is 4 to 1, so those 2 will be gone. So the compressed will be, now you tell me, S
0, 1,
0, 1, 1,
1,
A, B, C, D. Right? That's easy, right? Right, now 4, S 4, we are going to have 3 zeros. 0, 0, 0, and 1, A, B, C, D. We are going to have 4 additional digits that we really don't care. Right? So X, X, X. And the compressed will be S for the sign. 4. 1, 0, 0, right? 1, 0, 0, and A, B, C, D. I will write all this. Error is tedious, right? You already know how to do this, but I will write this. The reason is because we are going to use the example. So I'll let you do the real example with this table. 5 is, right? Now you tell me. S 0, 0, 5, we have only 2 zeros. 1, A, B, C, D, 4X, and the compressed will be S 1, 0, 1, and A, B, C, D. Totally we have 8. Compressed from 12 to 8. Then 6, that number is relatively large, right? How large? The first one is a sign. Then it will be 0, then we have 1, start from here, from the 3rd digit. Then we are going to have A, B, C, D, and 5 digit. We don't care. Okay? Then this one will be compressed with a ratio of 32 to 1. So that means 5 digits will be gone. All these 5x will be gone. So this one S here, and this is 6, right? 6 will be 1, 1, 0. So 1, 1, 0. Then A, B, C, D. And the last one, if the number is very large, it's the last one, that means it will be S, the sign, then right after F is followed by 1. That means this number is large, this input is. And then A, B, C, D, then we have 6 digits, and the compressed will be S, 1, 1, 1, and A, B, C, D. Okay, that's it. That is the process for digital compression. Any questions on that? Before I give you an example, let you do it. You look at this table. I'll give you a 12-digit number. 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. This is the original PCM 12-digit. 12-bit. How to compress this? With this mu255 or 13-segment compression. Step 1, you decide which segment is this on by determining the first one in addition to the sign, right? You don't count the sign. So the first one is always 1 here, right? That's the sign. We always copy this. So you don't even need to think. The first one is sign, put here. Then you decide which segment is this input on. Then you need to find out which one is the first non-zero, which means 1 here, binary, right? Where is the first one? It is here, right?
5.
And how many zeros we have before this? We have 2.
5.
So
5.
it is here, right? 0, 0, 1, 0, 0, 1. That's it. What is here? 5.
1, 0, 1.
1, 0, 1. What's next?
1, 0,
1, 0, 1. What's next?
1, 0, 1. Yeah, 1, 0, 0.
1. Like this? Yes or no?
I'm sorry, I got lost in that second.
You get lost, okay? So now let's. This one is the sign. You don't need to think, copy this. Then you decide how large this number is, or what segment is this number is on, by counting the zeros. How many zeros before the 1? You look at the first one is 1 here, so 0, 0, 1. If you want to use this table, then you just look at this. Sign 0, 0, 1, or not this. Sign 0, 0, 1. Oh yeah, this one. So the segment is 5.
So you like the one that first.
So that means it is the number is here, the input is here. So we can see the compression ratio will be 16 to 1. That means we are going to divide it by 16. Right? 16 to 1, so this is here, right? Then after the 1, the 4 digit will be ABCD that we need to keep. And the next 4 will be gone because we divided this by 16, shift the 4 digit, this 4 digit will be gone. Right? So that means this is correct. Right after 1, you copy 1, 0, 0, 1. This is A, B, C, D. And these are X, 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 X. We don't care. If this one changes to 0, you still get this result. If this one changes to 1, you still get this result. Make sense? Alright? If I give you another one, can you do by yourself?
Yeah.
That's easy, right? Alright. That is the process for compression. After we discuss expansion, then I give you example to do it. So here, this is where we stop here. The next one is expansion. This is at the transmitter. This is at the transmitter here. Transmitter. This is the original input. Definitely, the original input is analog. You get the analog for example, our voice. Then you sample this, you get a discrete value. For each one, last time we discussed, we compress directly in analog domain, right? But now we do this PCM first, like we discussed last time. And we do PCM first, we get 12-digit PCM code. That is. Up to this point, we do not have any compression. Now we do this digital compression, means we directly compress this 12-digit into 8-digit. By this method we just discussed. Then we transmit this 8-digit to the receiver. At the receiver, we receive the one of this code. Now we need to do expansion. We want to, suppose we receive this one, we want to get this from here. Right? Now this is expansion. It's called expanded, right? I call it recovered, or doesn't matter, right? Expanded code. How long is the expanded code? 16? 12, right? We want to recover back to the original, so that's 12. Originally is 12, compressed to 8, then you expand back to 12. Suppose we receive this one. Can you guess what is the original? Okay, definitely the first one is the sign. We cannot change that. So you put here. Now I need 12 digits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay? I need 12 digits. I put this comma here just for.
So it'd be three,
you can see clearly, right?
so it'd be 3 zeros, 4 zeros, and A, B, C, D.
So 3 zeros, 4 zeros, then A, B, C, D.
Yeah.
Right? We can cheat. Look at this. Look at this. That's it, right? Yes, 3 zeros, 4 zeros, and A, B, C, D. And A, B, C, D, that's A, B, C, D. Why is this? Because we do not have any compression for zeros, for the data on the zeroth segment. So it's this one we know there's no compression, so we just use A, B, C, D. Right? Make sense? Okay, now suppose the data we received is this one. The sign 0, 0, 1, A, B, C, D. If you, for example, work for some company, you write a code to automatically record this. You do not want to do it by hand, right? Because there are how many numbers in each second?
12.
Nick is the frequency, right? Twice of the highest frequency. For example, my voice, you need to have 40,000 numbers in each second, so you cannot do this by hand. You need to write code, let the computer do it. What you do is, the first line you ignore, that is the sign. You just copy it. Then you read in this 3 digit. Right? The next 3 is 0, 0, 1. What does that mean?
1.
This one means that's a segment, the index for segment. So that means it is on segment 1. And we know there's no compression. Right? So the form of the original data is 1 ABCD. So we have S here, 0, 0, 0, 0, 0, 0, 1, and ABCD. These are the record. We don't have compression. So do we have, yes?
Why did you say it's S000 and not S001?
Because this one is on the first segment, the forward may need to be like this.
Oh, okay.
This one must be 1. If this one is not 1, then it will be smaller than this. It will be on this segment. Because the 1 here, so that means this is larger than this one, right? Because this one here is 1, is 0. And this one is even larger than this, because this part is 0, this part is 1. So this one is twice as large as this one, because it's shifted like to the left by 1 digit. Any questions on this? Okay, the next one will be, suppose you will receive this one. Sign 0, 1, 0, and ABCD. Copy this. What segment is this?
2.
2. Why? Because the next 3 digits will be 0, 1, 0. So we are going to know, we are going to have how many zeros for this?
3 zeros in that section.
3 zeros, then 2 zeros, right? What's the next digit?
1 0. 1 0.
1 must be 1. No 1 0, only 1. Then what's next? A, B, C, D. Oh, we need one more. X. So X means you can put 0 here, you can put 1 here. That doesn't matter because this information is already lost. We cannot get it. So you either put 0, put 1, we have error here. That is called the expansion error. The next one here, if you receive this, then sign here 0, 0, 0, and you're going to have 1, 0 here. What's next? 1, and A, B, and C, D. What next? 2x. And you just randomly put theoretically, you put randomly 0 or 1. But that's not real. Later time we are going to have rules how to deal with these zeros. This x is not randomly. We have some consideration. Alright, so this one here, if you receive S100, so sign here, and again we have 3 zeros, and this one we are going to start with a 1 here, and followed by A, B, C, and D. Then we are going to have 3 additional X. Good? Alright, the next one is will be S000. Alright, no, not 0 anymore, it's 1 here. Then A, B, C, D, okay, 4X. And this one will be S0, 1, A, B, C,
It'd be S1.
D, X, 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 X.
It'd be S.
Right? That's the segment 6. Then the last one will be S1, A, B, C, D, X, 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 X. Right? We are done with the compression, the expansion. Any questions? Okay, now let's talk about this X. We really don't like this X. We need to put either 0 or 1. Theoretically, we said we can put anything because this information is lost. We don't know. Right? We have rules. We all for no matter how many X, the last one is always 1. All others. Let me see. I believe. Right? The first X must be 1. All others must be 0. That is the rule. Right? So that means this one here will be, this is the first X, right?
Yep.
We have only 1. Yes? That's why it will be 1. Make sure this is correct. Right? And this one, XX, 2 digit, we cannot use XX. Instead, we need to use the first one is 1. Then the next one all others must be 0. And this one, same thing here. So this one will be 1 and 0, 0, 0. Only 1. And so this one will be 1, 0, 0, 0. This one will be 1 here and all zeros here. And this one will be 1, 0, and 0, 0, 0, 0. Alright, so those are the correct recovered data. Do you have any questions to ask? Do you want to ask why we use this rule? Definitely, right? We said we have some consideration. Why we want to use this rule? Theoretically, we can use anyone. Why this one is the best? Right? Suppose a number. Let's look at this one. Suppose the number is S00001 A, B, C, D, and XX. We don't know. This two will be called the recovery error, right? What is the maximum error can we have? If you randomly put some numbers here, what is the maximum error can we have? We use binary, and because all these are binary. 3, right? For example, the correct data is 0, 0, but you put 1, 1 here. Right? That is 3. Or the correct data is 1, 1, but you decided to put 0, 0 here. So the maximum error is 1, 1. So that is if we have 2x, that means the maximum error will be 2 to the 1 minus 1, which equals 3 in this case. Right? How about the last one? We have 6x. What is the maximum error we can have? So that will be 2 to the 6 minus 1, right? Which equals 31. Because the number can be all 6 zeros, but you decided to put 6 ones. Or 6 ones in a real, but you put 6 zeros. So that maximum error can be 31. 31, we said this is binary. What is the real error? 31 what? Remember last time when we discussed the analog PCM coding? 31 is the error. Right? Remember, we discussed a lot of questions. Okay? So this one, 31, the error is in binary. What is the actual error? 31 what? This one 31 not boot, right?
R.
31R, perfect. Okay, that will be 31R. And this one will be 3R. Right? The actual value depends on your resolution. 3RV, 31RV. Now that is good. Does it make sense? So you can see, for smaller numbers, the error is small. For large numbers, the error is large, can be large. But we discussed the relative error. If you put like this one here, you always put one here. What is the maximum error here? If you put one here, then we have 5 zeros here. What is the maximum error? Again, we have only 1, 2, 3, 4, 5 zeros, right? If you use this way to make sure the relative error, all the relative error except this one, this two has no errors, right? All the relative errors will be the same. So that's the consideration why we want to use this one. Yeah? Any questions? Before we have a real example to do this. Okay? We have 3 problems for homework and alright? Not yet, right? Alright? And now this is the first one. I'll show you how to do this. Alright? So the question is the sampled voltage. The sampled voltage equals V equals 0.053 volt, right? And I want to use resolution of 0.01. And we assume 1, a leading 1 for positive.
What is some what?
Huh?
It says the sum what?
The leading one.
Assume a leading digit of 1 for positive number, for positive value. I believe you learned in 301 or something, use 0 for positive number, right?
Yep.
Right? And negative use 1 at the beginning, but this can change, right? So I use this one, right? What I want is, what is the 12-digit PCM code? What is the compressed code? What is the recovered code? What is the compressed error? What is the recovered error? What is the total error? So all 6 questions. The first one is the PCM code. Eh? You can do this. You need to recall what we did last class. Convert a discrete value into a PCM code. How to do that? Remember the example here? 8.65 or something, right? How to do that? question? Nicholas? Anyone? Remember this? You want to wait until the last day to study for the test, right? You can't. Right? I guarantee you're going to fail if you do that. So how to convert this into PCM? Use this number divided by the resolution first, right? So 0.053 divided by 0.01 equals 5.3. What's next? Round this to 5. Now convert this 5 into a binary, right? So 5 in decimal equals how many digits do we need? We said 12, right? We need 12 digits, right? And the first digit is the sign, because we assume 1 for positive, so this is 1. And we know this file is 101, right? So that is 101 here. Like this. Questions on this? Yes or no? Is this good? That's the PCM 12 digit. What is the error here? The extra error is 0.003, right? Make sense, right? And you can see this is 0.3 then times R. 0.3 times R is this one, so that's 0.00. Look at this. This one is 5. 5 means 5R, so that means 0.05, and we throw away this 3. So that is the error, right? Then we compress this. What is the compressed? Compress this 12 digit into 8 digit. 1, 0, 0. Why 3 zeros?
0, 6.
Because it is small, represented by the first one is here, right? So this small, so that's on the 0 segment, so that's one here. What's next?
0,
0, 1, 0, 1. Right? So that's it. That is compressed. Okay, the next one will be we transmit this and then receive this, then we expand this. The recovery. What is the recovery of this? We need to go expand this back to 12.
The first one, maybe
1, 0, 0, 0.
0, 0,
0,
0.
0, 0, 0.
And 0, 1, 0.
And 0, 1, 0, 1. Right, that's the recovery. Do we have any error here? No, because this is on segment 1. Definitely no, physically there's no error. From here to here, that's no. Alright, so that's it. Okay, let me give you another one. Suppose this number is, let me see, 95. I change this one to make it bigger. And you do the same thing. I change this one to 953. What is the decimal integer? 95. Good. What do you got that? Alright. Then what is the PCM code? The 12-digit PCM code? You need to convert 95 into binary, right?
Right.
So what is it? If you have a calculator, maybe you have this function, right? But you're not. That's very simple. So 95. The first one is 64. 64. Then the second one 32. That gives you 96. But 95, so it's one less. So what is it? 1 0
101.
1 1 1. How many? 4, right? 4 ones.
101 and then 4 ones.
Yes. 1 0 1, then 4 1. 1 0, then 4 ones, right?
1 0 then 5 ones.
1 0 5 ones. 1 0 5 ones.
Yeah.
Okay. So that is the original PCM code, 12 digit.
So you don't segment 5.
So up to this point, what is the compression error? What's the error? That is not called compression error. This is called what error is this?
Resolution error.
Not resolution error. It's something like that, but not quantization error. Make sense? Because we convert 0.953 into some digital, so that is called quantization error. So the error is 0.003, or you can say 0.3R. Eh? So that is the first error. So the PCM code is this is positive. So the first one is 1, then followed by several zeros, then followed by 1 0, and it's 5 ones. That's the original 12 digit. The next one you compress. What segment is this on?
5.
5, 4.
I believe it's
All right, let me write this number. All right, this number is
32nd.
95. It's this one is 1 0 5 ones. 1 2 3 4 here. 1 2 3 4 1 2 3 4. Like this, right? 1 2 3 4 5 ones. You said 1 2 3 4 1 2 3 4 1 2 3 4. So that is the original PCM binary. So what segment is this?
Third.
Third. Third segment. What segment is this? You look at the first one, except the sign. Then you compare with that. This one, okay? So you look at the first one, except the sign. Then compare with this table. So what segment is this? 3, right? It's at third, right? 3, yes? Okay, 3. Then what is the compressed code? That's the compressed code. The compressed code has 8 digits, right? The first one is 1. The next 3 means the segment. You just said the main segment is 3, right? So that will be 0 1 1. Is this good? Then after this one, A, B, C, D. Okay? This one doesn't count. This one gives us the information for the segment. Right? So after this one, then A, B, C, D. So So what next for?
All one.
What's next for?
0, 0.
0 through 1. Yes or no? Everybody agree? Everyone need to agree. Yes or no? Yes? Zero through 1. Yes? Yes or no? 0 through 1, right? Alright. So that will be 0, 3 1. Why? Because we start from this 1 here, followed by A, B, C, D. So A, B, C, D. These two will be X. Will be gone. On the third segment, we divide the input by 4. The compression ratio is 4 to 1. Means you shift to the right by 2 digits. Alright, now what's the recovered? We receive this 8 digit. We need to expand back to 12.
The same as the original, but with the same numbers.
Okay, so same as the original, this one. 1, 0, 0, 0, 0, 1, 0, 1. What's next?
1, 1, 1, 0.
1, 1, 1, 0. Because we don't know this, right? This is A, B, C, D. So this is A, B, C, D. That is the one determined by the index of the segment, which is 3. And this one. And these two, we don't know. Theoretically, we can put anything here, but by rules, we need to put the 1 as the first one and the 0 as all the remaining. So that's the recurrent. Question on that? Okay, now tell me what is the compression error? Huh?
1.3R.
0.3R, that is quantization error. What is the compression error? 3? That means the maximum error is 3, but we have a better algorithm. 1, right? 1 what? You cannot tell me 1. 1 is, you can see 1, but you need to explain more. 1 what? 1 R, right? So the actual error is 0.01 volt. Make sense? Everybody? Because the real is here, 1, 1, but we said the recurrent is 1, 0, so this part is the error. And this is 1, means 1R, means 0.01. What's the total error? Start from the quantization all the way up to at the receiver, you receive this, you recover this. What's the total error? We need to add these two together, right? And keep in mind, we need to know which one is positive, which is negative. The errors can be positive and negative. And this one is, this error is, the real is 5.3, but we use 5. The error is, we use your number, our number, minus the real, so that means it's negative 3. So the quantization error, error is negative 0.003. And that's only one. Right? Negative. And the compression error is, we recovered this. The actual is 1, 1. We recovered this one. So this error is positive or negative? The real is 1, 1. But we recover this as 1, 0. So we have 1 less. So the error again is negative or positive? Negative. Negative, right? So negative, that will be 0.01. Negative. And then the total is add up together. Negative 0.04.
So how did you get -0.03 out of that.
This one?
Yes,
Look,
because it's either,
oh, 0.03.
yeah, it looked like it was either a 0.03 or.
There's another 3, yes, you're right. 0.003.
Okay.
Because this one, 0.3 is here. That's the error. 0.3 R. R is this. So this one is the error. Because we implemented 95 here. This is 95. This is 95. So we use 95. Instead, the real is 95.3. So this one is 0.3 R. So we PCM encode this 0.95, and we forget this 3. So that is alright. So this one will be negative 0.013. So that's the total error. Alright. So error can be positive or can be negative. So, any question on this? Can you take the test? Good, huh? Okay, that's nice. Everything is in the slide. This one is not in the old slide, but I just revised this morning, so I may update the slide. So this one is also, but only the first one, right? not the second. Second one, just let you try. Looks like you need more hands-on exercise to do this. Okay, we finished the most important part. Now we summarize what is the PCM communication system is. So in the PCM communication system, the first one, we have analog signal here, like my voice or anything. And we use a band pass filter. We pass this one through a band pass filter. I will ask you why we need this band pass filter. The next one is, you can ignore this first. Suppose we have analog signal. What's the next step?
Multiply.
Multiply. We want to use this PCM communication. All this thing. So if you have analog signal, PCM means a digital, right? Postcode. You cannot directly transmit this, so you do not multiply, use the AM or FM, PM. We don't do that. This is digital. So the first step is you will need to sample this, right? Once you get this, you need to sample this. Make sense? Alright, so that is called sampling. And hold, so that actually is analog to digital. Sample and hold, so we get this code. Well, now let's discuss why we need this band pass filter.
To get this frequency cut off.
Right, to limit the bandwidth. Why? Because when we sample this, we need to satisfy the sampling theorem. The sampling theorem means the sampling frequency must be at least twice of the highest frequency in the signal. If you do not limit this, for example, if you have a noise introduced in here, that is possible, right? I'm talking here, there's noise here. Then this noise, we know the bandwidth of noise is very wide, ultra wide bandwidth. That means if we do sample this, we need to take care of the very high frequency component here. So otherwise, we are going to have aliasing. So that's why almost all, we need to use a band pass filter to cut off the out of band noise. Okay, we sample this, then we use analog to digital conversion. ADC. And this is a. We have this. Once anyone used the ADC before in what class 230 or 200? Have you used the ADC before? Analog to digital conversion. Okay, ADC.
Oh, yeah, that's in 230. Yeah.
Like this, you have IC. You used this before?
I haven't just got it.
Right. So that's at least that's the input. Okay, XT. Right. Now we are going to have output. Pins based on, for example, 16 digit. Then you are going to have 16 digit, right? And this one will be like the output will be parallel. So this one will be the 0, 1, 2, 3, all the way up to, for example, 15. So let's give us a 16 bit. Like example here, we use 12, but this one maybe 16 or maybe 32. 16 is more popular. It's very less expensive. But anyway, this one gives us a parallel output. When we transmit this, we want to use a sequential or series transmission. So we are going to have this output here. We are going to have a parallel to series conversion here. Right? Convert into only one. So like this, like this. This one gives us a parallel. So we are going to use this. So this is a series PCM code. Then we transmit this. After some distance, we need a regenerative. Because the amplitude of the pulse can be reduced by distance, attenuation, and also the quality can get worse. So suppose to be like this, good. Then we may get something like this. So we may have circuit here, regenerative circuit here. Then we may need another one. If your distance is very long, then we need another one. General circuit. Then finally, we have several here. At the receiver, what's next? We need to use because we receive this in a series. So we are going to have a series to parallel converter. All these are series, then I'm going to have like pins like this. Then the next one will be DAC conversion from digital to analog. So I'm going to have only one output. So that is what I have. Any question on that? Definitely in between here, we can use compression, expansion, all these techniques, but this is basically a diagram for PCM communication system. If you are reviewing a PCM system, you are looking for all these big blocks, these functions. Okay, we finished our PCM coding. There are some variations of PCM. It's related to PCM, but we do not call them PCM. In PCM, we know we use binary and 0 and 1s. And all those numbers represent the absolute number. For example, if you have how to determine how many digits should we use? You use 12 digit, use 16 digit, 32 digit, how many digits should we use? That is the dynamic range, right? So if your small signal is very small, your large signal is very large, that means dynamic range is large, then you're going to use a more digit. And we have, sometimes we do not need that absolute value. We need only relative value, right? For example, if the number is 0.1 or like 9, 8, 10, something like, suppose we have these numbers. if we want to PCM code this number, the smallest is 0.1, and the largest is 10. We need to consider all this, the range. But if, so we need to use more digit. But if the number is here, we start from 0 here, there's no 0.1. We only use these two numbers. You still use this number divided by R. So the number of digits is still large. Right? But if you look at these numbers, actually they are not that large in relative. Right? For example, everybody get 80s, 90s or something. The dynamic range is not large. So we are going to use a differential PCM. It's called differential PCM. We only code the difference between each one. I choose the minimum here. Suppose this is 8. I use this one as the base. Then what is this? This is 1 compared to this. What is this? This is 2 compared to this. So I will, this one is 0. I will code this one instead of this. Does it make sense to you? For example, everybody get a midterm, right? Everybody get like 80, 90 or something. Right? Suppose the minimum is 80. I can record 80, 81 or 100. I don't need to do like that. I can give you, for example, if you're 80, I just write 0. Right? If you're 81, I just write 1. I know everybody is relative to the base. So that's called differential recording or something. Here, we PCM code the difference of each one compared to a base. Then this one, the dynamic range will be reduced. So the maximum here equals only 2, instead of here equals 10. The idea is good, but the practice is nothing new, right? So you just use all the input minus the base, then we get a difference, then you just PCM encode the base, the relative values, that's it. That's called differential PCM. The other one is called delta PCM modulation. This one is even simpler than this one. Right? I only care about the sign. I'll give you some numbers: 5, 8, 7, 4, and 9, 10, like this. How I modulate this one with delta? I start from the beginning. This one I just give, for example, 0. The first one. Then the second one. This one, if this one is larger than this, I make it as 1. Right? So 8 is larger than this one, right? Right? I put 1. This one is smaller than this one, so I will put 0. This one is smaller than this, so I just put 0 here. And this one is larger than this, I'll put 1. This one is larger than, put 1. I really don't care the absolute value. How large is this? How small is this? I only care you are larger or you are smaller. That's it. So I only care about the sign. So that's called delta modulation. Then I only transmit 0, 1, 0, 0. There's ups, downs, that's all. Does it make sense? Okay, now can you tell me when are you going to use this? You will use this one in your single project. Last time we mentioned the pulse width modulation, right? When did you see this word? Except in this class. We use this one to control motors, right? Can you use this method to control motor? Yes, right? If you increase, for example, the voltage, then you just put a 1 to the motor, right? If you decrease, then you just like this. So I think we can use this one to also control. And this one, the beauty of this one is the circuit is very simple. Just up and down, that's all. Okay, I think we have done this chapter. So any questions? Okay, thanks.
Yeah, yeah.